For our last inheritance pattern, we're going to be talking about X-linkage. X-linkage is a very particular type of inheritance pattern, not because of the way the genes are expressed, but mainly because where they're located. For X-linkage, we're talking about genes that are only found on the X chromosome. So these genes, being only on the X chromosome, make them kind of special because when we talk about X chromosome, it does matter whether you're a male or female. If you recall, in humans, we have 46 chromosomes, which when we pair them all up, equals 23 pairs. Now, we've been talking a lot about pairs of chromosomes, the fact that one has to come from mom, one has to come from dad. During meiosis, the chromosome pairs split, leaving us with 1/2 in the egg for mom, 1/2 in the sperm from dad, so that when fertilization happens, they recombine, bringing the chromosome set back to that happy number. Well, for pairs 1 through 22, mom and dad are exactly the same. Everybody has homologous pairs, and we call these autosomes. Up until this point, this is all of the inheritance patterns, all of the traits, all of the problems you guys have been doing have been all autosomal. It hasn't mattered whether they've been male or female, all homologous pairs. Well, pair 23, as we call it, is very special. That's your sex pair. And with the sex pair, if you're a female, your chromosome pair looks a little something like this. And if you note, oh wow, okay, they're the same. Same length, same gene placement, same everything. We have a homologous pair here. Nothing new. This is all stuff that looks familiar. Well, guys, I hate to break it to you, but for males, it is a little bit different. For males, you're going to have one that looks just like the females, and it's going to look the same there. But your other partner in that pair looks a little something like this. And so since they are not the same, we say that they are non-homologous. And instead of giving them a number like chromosome 23, because we wouldn't know what to call the males, we've literally called it X. So for females, your last homologous pair has 2 X's. Guys, you have an X. And so because it's not an X, we've gone and called it a Y. So that designates males from females. And there's a special gene on the Y chromosome that's called the SRY gene. And that's sex determining. During embryonic development, this gene turns on in guys, so setting the course of events for you to become a boy. The gene doesn't turn on, you're going to be stuck being a girl. So when we look at X-linked genes, we're going to talk about genes that are only on the X chromosome. So as you can tell, it's a little different since girls have 2 and guys only have 1. So we're going to start first off by, I just want to give you guys a reminder of the rules to know a problem is X-linked. Because these inheritance patterns, they're dominant recessive, so you need to know whether or not you treat it as an X-linked problem or whether you have to treat it autosomally. So the rules are, if the problem has anything to do with hemophilia, hemophilia is a recessive disease. It's where you don't have the ability to clot or stop your bleeding. So someone with hemophilia really has the potential to bleed to death in minor injuries because they lack that ability to clot and stop their bleeding. This is a gene located on the X chromosome. So if the problem has anything to do with hemophilia, X-linked. The second one, red-green color blindness. Is also a recessive gene located on the X chromosome. So if the problem has anything to do with color blindness, X-linked. Third rule, because the problem says so. If you want a reference on this of what that might look like, look at your X-Linked worksheet that you guys got in class and look at question number 8 about the fruit flies and their eye color. Question number 8 states the question in a way that would share with you that this is an X-Linked problem. All right, so we'll do our example today taking a look at hemophilia. So hemophilia, as I said, is a recessive trait. So for somebody who has the dominant allele, their blood clotting is normal time. They can clot their blood. No worries, bumping into a chair isn't going to hurt you. If you carry the recessive allele, you're going to have hemophilia. Okay. Now, because this is on the X chromosome, we have to write this very specially. So if I'm a female, we use the letters X's for both. We're going to use X's. And we'll designate whether or not the allele is the dominant or the recessive by putting it up in the corner like we did for codominance. So if a female is homozygous dominant, we'll put the H's up there, they're normal. If they're heterozygous, they're normal. But you may also see them referred to as a carrier. Okay? If they're homozygous recessive, they have hemophilia. Now, this looks really familiar. There's nothing new about that, about how a recessive trait is expressed. You're going to really see the difference when we look at males. Okay? Because males, again, they're XY. So for a guy, he's only got one. I put nothing up in the corner of the Y because this is not a gene on the Y. So for a guy, they either have it or they don't. They have one X. So if a guy has the dominant, they're normal. If a guy has the recessive, he has hemophilia. Okay. And this is why in a recessive X-linked trait, you're going to see significantly more males than females who have this trait. So if we take a look at an example where, let's say we have a normal man, okay, marries a carrier female. Okay, 2 questions will come to mind. Let's go with, what is the chance their first child will be a normal girl? Because in X-linked, not only do we have to designate whether they have the disease or not, because this deals with the sex pair of chromosomes, we have to know their sex too. Do they have the disease and are they a girl? Do they not have the disease and a girl? You know, do they have it and have a boy, and so on? So we're going to take a look at that question. I'm also going to ask the question, cross that, if their first child is a boy, what is the chance he will have hemophilia? Alright, so again, as you've heard me say, the steps are all the same. Let's figure out the genotypes first. A normal man. Well, a normal man means he doesn't have it, which means he has to have the dominant allele. So dad is going to be X, big H, Y. Marries carrier female. That tells me that she doesn't have it either, but she is heterozygous. So there's your parents for this particular cross. I'm just going to rewrite the parents up here since we're going to a new page. Alright, so we look to the gametes. Well, dad's either going to give an X or he's going to give a Y, and his X will have, on his sperm, he might have the dominant allele on the X chromosome. His other sperm is going to have a Y in it. For the female, she's going to have one with the dominant allele, or her other egg, possibly, depending on how things separate in meiosis, she could have the recessive. So you take your gametes just like we've done, and you use them to set up your Punnett square. So we get X big H, X little h for one parent, mama across the top. We'll put dad down the side over here, and then make your Punnett square. And then we look to interpret and answer our questions. Well, the first question asked, what is the chance that their first child will be a normal girl? So when I look at the overall outcome, and I look at all four possibilities, the chance that they're going to have a normal girl, well, she's going to be normal, XX, and she has the dominant allele, and she's going to be normal. So the chance that their first child will be a normal girl from question 1, the chance there is they've got a 50% chance, because all of their girls will be normal. Because no, dad is always giving his daughter the dominant allele. So anytime they have a girl, she will be fine, except in one case, she might be a carrier, though. Now, the second question is if their first child is a boy. So here's where the questions kind of change a little bit. We know that this first child's going to be a boy. So when you have a situation where you already know the sex of the child, you can ignore the other options. So I'm only going to look at my boys here. I know it's already a boy. So what's the chance he's going to be a hemophiliac? So I'm only going to look right here at the options for boys. And out of my 2 options for boys, so if my first child's a hemophiliac is a boy, what's the chance he's going to be a hemophiliac? Well, we got a 50% chance there also. Okay, because I'm only looking at the boys. You know, if mama goes in and she finds out that she's having a boy ahead of time, you know, she might ask, all right, I'm having a boy. What's the chance that he's going to have hemophilia? Because she's a carrier. And the doctor would tell her it's a 50% chance that this boy has hemophilia. So that's how it works. So when you're looking at the question, be really careful about the question. In the question, do you already know what the sex of the individual is? Or do you not know, and then you have to look at the overall? So there you have it. Those are all of the inheritance patterns and types of problems that we are going to cover this unit. So go back, take a peek at any of the other ones. This makes for good practice. So, you know, once again, if you're having trouble, make sure you're going and talking to your teacher and getting the help you need. So take care and thanks.